Hello again everyone. We're just about to start an exciting new section for this conference. It's called New Technologies in the Real World, where our networks will be sharing some of the new technologies that they've rolled out as business as usual, or BAU, after having tested them through various NIA and NIC innovation projects. It's pretty quick fire, so each presenter is going to have just 5 minutes to talk through how their fast follower technology works, the benefits they've seen from using it, and how other networks might look to implement it in the future. As usual, don't forget to ask questions via the Q&A chat facility in the window. And without further ado, I'd like to now hand over to the innovation project leads from our networks for this session. Thank you.
I'm Andy Howard. I'm the Innovation Programme and Smart Street Project Manager at Electricity North West. And today's presentation is about Smart Street Innovation Rollout Mechanism and what we're doing to support vulnerable customers in the North West. Smart Street was a low carbon network funded project from January 14 to April 2018. In the project we developed an awful lot of learning, some things that went well, some things that went poorly. Smart Street IRM is taking all the positives from that project to implement that proven technology and to integrate it with Electricity North West systems. The Smart Street project is targeting Electricity North West's vulnerable customers, and we're doing that to reduce their energy consumption. We're reducing the electricity losses on our network, both of which provide carbon benefits, and we're also creating capacity for new low carbon technologies to connect to our network. Smart Street is an element of Electricity North West's leading the North West to a zero carbon future. One of our strategies that, working with our stakeholders and various partners, we're looking towards pathways to a low carbon future. So how are we targeting vulnerable customers? Well, we're using lower level super output data for the North West to find the fuel pool, and we're targeting investment in substations in those particular areas, associated with other limits such as current uptake of LCTs and predicted future uptake of LCTs, and a number of technical constraints that we have in our selection process. The project is all about conservation of voltage management. It's about improving voltage control and management on our network, being able to optimise the voltage on the network to provide those energy benefits for our customers. Technically, what Smart Street is about: firstly, it's delivering 180 on-load tap changing transformers into our distribution substations. These are a mix of 11,000 and 6,600 kV transformers of mixed ratings, and they're all cable connected. These will be able to control the LV voltage by up to 20% around the nominal tap position. Standard transformers only allow us a 10% control. These tap changes will be allowed to tap on load, so we control on a regular basis what the output voltage for the LV network is. We are also meshing the LV network together. At up to 720 LV ways, we will be replacing the standard fuse with an LV circuit breaker. Those circuit breakers will be able to be remotely controlled and provide measurement data from the substation, such as voltage and amps on the LV way. We will also be installing LV switches in remote link boxes that will be able to mesh these LV ways together. Finally, there's a communication and integration element. All these new devices will need to talk to our network management system, our control room systems, and then we will be implementing some optimization software within that control room system that will allow us to take the readings from site, model what the network is up to, what the optimum position should be, and then issue controls from the control room system to put that into place. So in terms of progress, where are we up to? Well, for the transformers, we had to go through a review of our internal policies and a procurement exercise. But now all 180 transformers have been ordered, and the first one has been delivered to Electricity North West, ready for installation. Some of the challenges we face there is, yes, the actual policy and procedures to get those implemented, but also how we're actually going to integrate this new technology into our NMS system. In terms of the LV network meshing, again, we went through a policy and procurement exercise, and again, the LV circuit breaker element of that project is being delivered today, ready for installation. Again, the issue we have at the moment is integrating that with our NMS system, but also some of the devices we're purchasing, we also use in the business in a slightly different way for quality of supply. So one of the challenges we have is integrating two systems to give combined benefits. Finally, in terms of the optimization software, our focus at the moment is ensuring that all the devices are going to fit. We'll talk to our control room system. We have, however, gone through the specifications for what we require for the optimization software and gone through a lot of the integration about how that will work with other key systems and processes. So in summary, where are we with the project? Generally, we're on track, and indeed a number of items in the project are going to be delivered earlier than anticipated in the IRM bid. We are about to commence the installation phase and get our first installations. So this is going to be a challenging time for us as we test that all the good planning that we put into place actually works. Although we envisage there will be some more learning that we'll need to embed in our policies and procedures and use to develop our training material so that these devices become a business as usual activity.
Hello, my name's Kevin Dennis and I'm a project manager working for Scottish and Southern Electricity Networks. Today's presentation is focusing on a project that's currently ongoing within SSEN, Low Voltage Underground Fault Location Technologies, Lvflt. SSEN's innovation portfolio takes on 5 category areas: connections and capacity, reliability and availability, the environment, customer service and social obligations, and safety. The Lvflt project takes into account 4 of these areas: reliability and availability, the environment, customer service and social obligations, and also safety.
This slide is to explain the origins of the Lvflt project. At the bottom of the screen we have our fault finding operative. The operative is faced with many challenges on a daily basis. Have I excavated in the right place? The cost of supply restoration and CML fines on getting customers back on supply, all under the umbrella of the LV fault finding challenge of correctly identifying the fault on the network the first time. Scottish and Southern Electricity Networks over the years have been building the toolbox that the operative will have ready to go out and finding that fault. We've looked at thermal imaging camera, which has utilised the heat given off by the fault. We've also utilised the cable sniffer, a smell, and the HASIS device, bringing about the phase identification. All these tools in the operative's toolbox to go and help them. But the one thing we haven't looked at, of which Lvflt was to utilise, is acoustic. We were aware of acoustic fault finding equipment on the HV network, and part of the project was bringing about the acoustic technology onto our LV network, but at the same time incorporating all our existing works that we've done within the business. The outcomes are on the next slide. Lvflt in practice. This following slide shows what happens when you combine the existing toolbox, the thermal imaging camera utilising heat, the cable sniffer utilising smell, and the HASIS utilising phase identification, with the now acoustic device utilising harmonics to detect the fault on the network. The LV fault comes in, clock's ticking, where will you dig? With the van loaded with the new toys, acoustic, thermal, smell and phase identification, with operatives trained for using processes, supported, the mobile app, we found that we had a positive result and we had a reduction on excavation spend, reduction of CMLs and reduction of spend on additional operatives.
Thank you for taking time viewing this presentation. If you'd like any further information about this project, come and visit me, Kevin Dennis, at the SSEN stand at the ENIC conference this year. Thank you and look forward to seeing you then.
Hello, my name's Gordon Wilson. I'm an innovation engineer at National Grid, and I would like to thank you for the opportunity to talk about a project that we completed earlier this year and have already implemented into business as usual. I'm going to spend a few minutes telling you what we were trying to achieve, what we did and how we have delivered. The outcomes of this project are not only of value to National Grid, but potentially have value for other transformer owners. The aim of the project was to fulfill a need where we have small numbers of transformers of many different designs. Each of these designs have specific requirements for bushing terminations at 33 kV. They can vary in the required ratings and geometries, or in the internal connections, and they can be based on either imperial or metric measurements. Well-designed transformers can remain on the network well beyond their original design life. We have many transformers now that are over 50 years old, and some that are over 60. During these long lifetimes, the bushings can develop problems that mean they need replacement. Bushings are designed to be replaceable items, although it's not always particularly easy. To facilitate these changes, we hold spare bushings in stock, because lead times can be several months. However, holding, say, 3 bushings for each transformer design requires significant financial investment in stock that is turned over only very occasionally, when the number of transformers of each design is fairly small. In addition, beyond the capital cost, spare bushings need testing and recertification every 7 years. We wanted to reduce our stock holding of 33 kV bushings by having a single design that could be installed on all transformers which were supplied to BEBS T2, a specification for transformers that was in place across the CEGB and still in use until the 1990s. You can see here on the left an example of a transformer with 33 kV terminations, and here on the right a closer look at a conventional 33 kV bushing, one that is porcelain clad and oil filled. So for this project, National Grid engineers set about developing a solution that could not only reduce our spares holding, but might also make installation jobs easier, and by meeting modern standards for bushings, reduce risks in operation. The risks are reduced because the oil was removed and the porcelain cladding was replaced by silicone rubber. We worked closely with a designer and a manufacturer to find innovative solutions where all parties brought their experience into the project to get the best solution possible. We always knew we would end up with bushing kits as a solution, but we wanted the number of components to be minimised, and everything needed to be easily assembled for each job. Once we had manufactured the bushings to the final design, they were put through their paces in a number of tests to meet our internal requirements for new bushing designs. All of the tests met the requirements and were approved for use. As part of the project, we delivered the first 6 bushing kits ready for use into our strategic stores. Because the 6 kits will cover all the designs necessary, the holding has been reduced from around 30 to these 6, so we hold around 20% of what we would have needed for the conventional designs. You can see an early concept design here in the top left. The drawings are the final designs for the main body of the bushing, and the different parts required to modify the bushing to fit in every instance. The final boxed kits are shown here in the bottom right. All 6 of those bushings have already been put to good use on transformers at 2 of our substations. The kits were delivered to site and the adapters selected appropriate for the needs. The bushings and adapters were assembled easily on site with push-fit and lock connections, and the installations were made easier by the new bushings being lighter than those they were replacing. All 3 new bushings were installed in around 90 minutes, which was less than we expected, especially for the first job. Once the job was complete, the rest of the kit was sent back to stores so that the used components could be replaced. Whilst National Grid has already benefited from achieving its goal on this project, we fully expect that the interchangeable bushings that we have developed would work on other transformers with 33 kV connections. In our case, 33 kV is on the LV side, but we anticipate that these could be used on the HV side of other network transformers, of which there must be many in the UK. Thank you for listening.
Our world is changing rapidly, with decarbonisation and the constant development of new technology at the heart as we look towards our net zero and climate change ambitions. However, the transition to a greener lifestyle and the increase in low carbon technologies like heat pumps and electric vehicles is resulting in an unprecedented demand on our electricity network. As the operator of critical national infrastructure, our focus at SP Energy Networks is to continue to innovate, modernise our network, drive decarbonisation and digitalisation initiatives, and so much more to meet that demand and provide our customers and communities with a safe, secure and reliable electricity supply now and well into the future. Finding innovative solutions to enhance our network visibility and smarter, more agile ways to manage our operations is therefore critical. One such solution has been a recent development of a Network Innovation Allowance funded project known as Identify. Developed over 7 months as a successful proof of concept, Identify uses artificial intelligence recognition and smartphone combination to help identify network assets and customer devices in a completely new way. Users will simply point their smartphone camera at the network asset. The intelligence of the app will recognise the asset type. The app will use the phone's own geolocation to determine the asset whereabouts. Then, with a tap on the screen, this combination of data is returned to us as the network operator. The Identify concept was proven via testing on one of the most common components on our distribution network, cable heads. Installation of these assets designed to cut off the power due to overloading or overload faults has gone on across our network for over 120 years. We now have over 3 million in operation, and whilst each of them was seen as state-of-the-art technology in their time, some were never designed to cope with the power-hungry, low-carbon technology we're seeing connect to our network today. It's therefore important, as the network operator, that we have an up-to-date record of the location, condition and suitability of these assets, allowing us to maintain a robust and reliable network by having complete visibility of high loads, the anticipated impact on the network performance, and therefore arming our engineers with information to make better informed decisions and take action as required. The Identify app not only allows us to effectively and efficiently gather up-to-date asset information ourselves, it also enables this asset data to be crowdsourced by third parties, for example, by those installing low-carbon technologies such as EV chargers and connecting them to our network. Their use of the app to share this data with us enables us to remotely assess the impact of these customer devices on our electrical network. Operational benefits like this are invaluable for our network of the future, but we're also exploring further use of the Identify technology to directly enhance our customer experience too, to reduce aborted check for safety call incident numbers and therefore reduce costs. Through remote intelligent asset identification, we could help customers identify third-party assets such as a telecoms cabinet and therefore direct them accordingly, or even offer guidance on faults they may be able to rectify themselves, such as tripped switches in their fuse box which they can resolve to bring the supply back on instantly without the need for one of our engineers to visit. This is an industry first for this type of technology, and we're excited by the results the proof of concept has delivered for us already. With the DNOs trying to solve the same problem, it looks like the SPEN Identify app will become the industry standard that all installers will be asked to use to check cable heads for suitability and report the installation of customer devices to each of the DNOs, which would be a welcome replacement to the existing paper forms.
Hello, my name is Ian Cooper and I'm the Innovation Lead at UK Power Networks. We keep the lights on for 19 million people across the east, the southeast of England and London. We're responsible for connecting distributed generation, or DG, onto the grid, and we've currently got about 9.5 gigawatts of generation connected to our network from 132,000 volt power stations down to the solar panels on your roofs. Today, I want to talk to you about a solution that we've trialled through an innovation project and are rolling out across our business called load blinding. Load blinding means that we can connect more distributed generation onto our network faster and at lower cost than alternative solutions. Our customers told us that it was taking too long and costing too much to connect low carbon generation to our network. So back in 2011, we sought funding to trial a number of new techniques in our flexible plug and play project. The £9.7 million Low Carbon Networks Fund project ran from 2012 to 2015 and proved the benefits of a number of new techniques, including active network management and flexible connections for DG, both of which are now business as usual at UK Power Networks and at other DNOs. Flexible plug and play designed, trialled and assessed load blinding as a possible solution to resolve DOC constraints. Since the project completed, we've carried out some further trials, we've developed and had approved all the required standards and documentation for the solution, and adopted load blinding as a reliable and low-cost solution to resolving DOC constraints, where that limits the reverse power flow on our network. Load blinding means that we can connect more generation to our network faster and at lower cost than alternative solutions. This helps us all to keep costs down as we travel along the road to net zero together. Quite often on our 132,000 volt and 33,000 volt networks, we use a technology called Directional Overcurrent Protection, or DOC for short, to detect upstream faults on our network. This can limit the amount of power that's allowed to flow upstream through a transformer, and this might be lower than the thermal limit, or the amount of power that the transformers, cables and overhead lines can cope with. It can also limit the amount of generation that we can have connected, as if there is too much generation, it could cause a high enough power flow to trip the directional overcurrent protection. Load blinding is a protection technique that leverages the significant difference between load or generation power flow and fault power flow. Specifically, these have different power factors, meaning that a modern protection relay that can measure and analyze the power factor can reliably distinguish and discriminate between network faults, which is times when you want the protection to operate so that the fault is cleared safely, and generation or load, which is when we want the network to remain connected so that the power can flow from the generators to our homes. This means that in many places on our network where there are reverse power flow constraints that are caused by directional overcurrent protection, we can replace the protection with modern relays with load blinding capability and enable more generation to connect more quickly at lower cost up to the thermal limit of the equipment. As said before, load blinding relies on load or generation power factor being clearly distinct from that of a fault. And this isn't always the case, especially if the distributed generation is providing reactive power services or other services such as those being trialled within our Power Potential project. So it can also be an issue at sites that are fed from multiple grid supply points with different major network configurations, because the different power flows at these sites can also cause different issues for load blinding. And so in those cases, the protection and the settings need to be able to be configured dynamically to cope with the change in the network conditions. At UK Power Networks, we're actively innovating to overcome these challenges in the future. In a digital substation, it's possible to download the protection settings, modify them, and then to reload them back into the relay. And this is something that would enable the substation to dynamically change its protection settings configuration to cope with a dynamic change in the network in the future. So we're continuing to innovate to provide the best possible service that we can to our customers at lowest cost as we travel together into the net zero future. Thank you for listening.
Well, sadly, that concludes New Technologies in the Real World. I thought it was a really great session. I hope some of you will walk away from this with new ideas that you can investigate and implement within your own organisations. So next up, we have our live exhibition stand session, where you can have a chat with project leads, innovators and other people in the exhibition and innovation halls. The stands in there are really cool. They have an extraordinary wealth of additional content and it's all downloadable. Don't forget to keep an eye out for the pop-ups on your screen at around 3 p.m, which will navigate you through to our group chats. One of these will be on power electronics, hosted by UK Power Networks, and the other will be on flexibility and stability for remote communities, which will be hosted by SSEN. Otherwise, we'll see you back here at 3:30 for the next session on smarter asset management. Thank you.